Dynamics is the study of motion and the forces that interact with moving objects. As we've seen before, Sir Isaac Newton basically owns this domain of physics. But now let's heat things up, shall we? What about thermodynamics? The physics of energy transfer and heat? The prefix thermo basically means relating to heat. You know, thermostat, thermometer, thermonuclear bomb. These are related to heat and our understanding of thermodynamics. But what is heat? To answer this, we must first realize that stuff is made of atoms. Protons, neutrons, and electrons compose these teeny tiny atoms. But there's a whole lot of stuff out there in the world. How can different configurations of collections of atoms constitute our variegated universe? This book, glass of water, and can of air are three completely different things, yet they are all made up of teeny tiny particles called atoms? Well, yeah. The reason these objects are so different is because they are each made up of different types of atoms, meaning the number of protons in each of the atoms that make up these substances is different. And also, the distance between the atoms in each of these objects varies greatly. In the book, the atoms are strongly attracted to each other electrically, and hence are closely packed together, giving the object its definite shape and volume. The particles don't move around much. They only vibrate about their individual fixed positions. This book is called a solid. In the water, the particles are less strongly attracted to one another. They're farther apart and wander around quite a bit more, therefore. As a consequence, water has no definite structure and shape, though it does have a definite volume. Water is a liquid, and in the air, the atoms barely feel any attraction to one another at all. They are separated by large distances and move around faster and very randomly. Air has no fixed volume, shape, or structure, and particles fit any container they are put in. Air is called a gas. Solids, liquids, and gases are the three states of matter. Any object out there, any object, can change its state of matter. Take this glass of water. The water atoms are separated, on average, by a certain relatively small distance. If we alter that distance, the water can transform its state from liquid to either gaseous or solid. How can we alter that distance exactly? Well, we add energy to the atoms. How? Well, of course, we push the glass and increase its kinetic energy. Just kidding. That's not how it works. Each of the water molecules in this glass has some kinetic energy, as it has some ever-changing velocity. But pushing the macroscopic object that is the glass won't increase the kinetic energies of these individual atoms. The average kinetic energy of these water particles is called the temperature of the water. When we feel that an object has a high temperature, it is hot. And when we feel that it has a low temperature, it is cold. Temperature is usually measured in degrees Celsius. Those are the units. Right now, the temperature outside, basically the average kinetic energy of the air particles, is about... Ooh, that's pretty hot. To turn this liquid water into solid, we must decrease the temperature of the water. To turn it into gas, we must increase the temperature. We ought to manipulate the kinetic energy of the water molecules. Let's say we put this glass in a very cold environment, like a freezer. It is surrounded by really cold air that has a very low temperature. Now, what will happen is that the particles of the water will bump into the particles of the air and cause them to increase their velocity. In this process, the water particles will lose their velocity. This is the conservation of kinetic energy. Eventually, the air will gain most of the kinetic energy of the water particles, and the water will slow down as a whole, and their temperature will therefore decrease. They will clump together and become the solid form of water. Their state of matter will change. It will become ice. Conversely, if we placed the water in a hot environment, the water particles will gain energy and speed up, and the distances between them will grow. It will become the gaseous form of water, steam or water vapor. This transfer of temperature of kinetic energy is what we call heat energy. In both situations, heat flowed from the object of higher temperature to the object of lower temperature, from the hot object to the cold object. Through this transfer of heat, the state of matter of objects can change. On a winter morning, you will see mist on the windows. This is just the hot, moist steam present in the air coming into contact with the cold glass and liquefying into water by a drop in its temperature. So, heat transfer. It's the transfer of kinetic energy from one set of particles to another. Heat is a form of energy. It's measured in joules. Therefore, say you place a pot of water over a flame, the temperature of the water will immediately begin to increase. And on the basis of that, you can calculate just how much heat energy you are supplying to the pot using this equation. Q equals mc times delta T. Q is the heat energy supplied, m is the mass of the object being heated, here it is the 5 kilogram of water. Delta T is the change in temperature caused by the supplying of the heat, here it's the temperature of the water increasing. C stands for specific heat capacity, which is basically the amount of heat you would need to supply to 1 kilogram of water to heat it by 1 degrees Celsius. The water in the pot has a mass of 5 kilograms and you heat it for 30 seconds. As a result, the temperature increases from 20 degrees to 90 degrees Celsius. With this information alone, we can decipher how much energy you supplied within those 30 seconds to increase the temperature by so much. You just plug in the values. M is 5 kilograms, delta T is 70, because 90 minus 20 degrees is 70 degrees, and C is equal to 4,200 joules per kilogram per degree Celsius. This means that the specific heat capacity of water is 4,200 joules over kilograms degree Celsius. It takes 4,200 joules of heat energy to heat 1 kilogram of water by 1 degree Celsius. That is a lot. Anyway, plugging in the values, we see that the total energy supplied within those 30 seconds of heating was equal to 1,470,000 joules. That is a lot of heat energy. This flame is incredibly powerful and the liquid water will rapidly turn into gas. Once it turns into gas, heating it will not really have any effect. All you will do is increase the temperature. There will be no change of state. When you heat a gas, no change of state is possible. Or is it? Say you keep heating the gas and its temperature soars. The particles move around in a freaky frenzy. Eventually, a process called ionization will occur. The gas will become so hot that the atoms in the water vapor will be stripped of their electrons. What you have now is a blazing hot mixture of freely flowing positive and negative charges. This is no longer a gas. It is a different state of matter, a fourth state of matter called plasma. Any gas, when heated to a hot enough temperature, becomes a plasma. Plasmas show very weird behavior as they respond to electric and magnetic fields, unlike normal states of matter like solids and gases. Plasmas may seem unfamiliar, but they are not rare. 99.9% of the universe is made of plasmas. Plasmas are what you'd find in the core of the very, very hot sun that supplies us with light energy. Now, let's return back to gases. Imagine we have a box with 3 particles of any random gas. The particles are A, B, and C. Each of these particles has some energy. It doesn't matter what kind of energy it is, it just has it. And let's suppose that that value of energy possessed by each particle can only take on specific values. It can't be anything random. We can represent the energy of each particle using this diagram of energy levels, as it's called. The least possible energy that a particle can carry in this scenario is called x. The second least is 2x, the third least is 3x, and the highest possible energy is 4x. No particle can have more energy than a value of 4x, and no particle can have an energy value that's less than x. Now, let's say that the total energy of all 3 particles in this box will always be equal to 4x. This means that the sum of the energies of the 3 particles will always be 4x. Now, can we draw out all of the different energy configurations of the particles in the system that satisfy our assumption that the total energy is 4x? Yes, indeed, and these are the different configurations. In all 3 of the configurations, each particle has a specific energy, and the total energy is always 4x. And none of the particles can ever have any energy value in between these energy levels. Each of these configurations is called a microstate of our system, and our system has 3 microstates. If we take the natural log of the number of microstates in our system and multiply it with a constant called Boltzmann's constant, we get a value called the entropy. of our system. What is this entropy? Entropy is often thought of as a measure of disorder, but really it's a measure of how energy is distributed within a system. For example, within this box of particles. Entropy is linked heavily with the number of possible microstates a system can be in. The greater the number of microstates, the greater the entropy of a system. The thermodynamic quantity of entropy has many consequences, particularly with regards to our understanding of time. The entropy of a system tends to increase. The entropy, the disorder of the universe, is increasing. And that's basically the second law of thermodynamics. The first law of thermodynamics is that energy is always conserved. It can never be created nor destroyed, and only be converted between forms. Yeah, and that's also, by the way, the law of conservation of energy. Hi, thank you for watching this video. If you feel certain explanations weren't understandable, or you have any questions related to them, please write to me in the comments section or through Gmail. If you'd like to know which resources have been used to research and create this video, I've linked a document containing them underneath. I've also linked a short worksheet that you can solve to test your understanding of this topic. Goodbye.